Okay. Well, I'm
Okay.
happy to be here. Yeah, it is lunchtime, so I hope some of you are actually enjoying your lunch, and I hope you can't hear my stomach growling because I can feel it coming on. I do not miss a meal. Um, Today I'm just going to share with you some very basic information about soils. Soil really allows us to feed the human population. It's really the basis of life on our planet, along with sunlight and water and our atmosphere. It plays a very important role in filtering rainwater that percolates, and some of that actually becomes groundwater recharge. It's really important in global nutrient cycles like phosphorus, carbon, and nitrogen. And so I'm hoping that when we finish today, you'll have a little bit of a basic understanding of soils and maybe an appreciation for soil. So 2015 has been the International Year of Soils, and the Soil Science Society of America has had numerous events and projects throughout the year to celebrate soils. And today we are going to follow this basic outline. We'll talk about what is soil, where does it come from, color, texture, and structure characteristics, soil as it relates to rangeland productivity, and then some technical tools that you can use to learn more about your soil. So what is soil? We walk on it all the time. We manipulate it to grow food. We build on it. We drive on it. But I think oftentimes it's taken for granted. And it is fairly simple at some scales, but also quite complex. So soil is predominantly mineral matter, and depending on where you are, there's relatively different amounts of organic matter mixed within the soil, and then the remainder is occupied by varying amounts of air and water, depending on when the last rainfall event was. But soil also is truly a living organism. In a teaspoon of soil, there may be billions of microorganisms, and those include bacteria and fungi, algae and protozoa, and those are all really important in nutrient cycling, especially uh, fixing atmospheric nitrogen, converting it to ammonia or nitrogen dioxide so that the plants can use it, decomposition of organic matter, which also makes more nutrients available for plant uptake. And then there are the macro fauna like nematodes, earthworms, termites, ants. Those all play a very important role. And soils are classified in much the same way that plants and animals are. If you'll remember from biology, the plant taxonomy is kingdom, phylum, class, order, family, genus, species. Well, soils also are classified in a similar manner. So a soil order, of which there are 12, is comparable to a plant phylum, and a soil series, which is a term that probably many of you are familiar with, is comparable to a plant genus. And soils are classified, these orders are determined based on one or two physical, chemical, or biological characteristics that distinguish it from the others. They all end in SOL, which is a Latin suffix for soil. So, for example, vertisols have they're prone to shrinking and swelling. They have large vertical cracks. Mollisols are thick, dark soils. Aridosols are soils that occur in dry environments. So each of them has a distinguishing characteristic. And Texas has a state bird, we have a state flower, we have a state grass, but we also have a state soil. And our state soil is the Houston Black. And I know this print is kind of small, but the Houston Black series occurs in the Blackland Prairie, and you can see from the map here where that occurs. Let me grab my pointer. There we go. This shows the occurrence where this soil series has been described, and it says that it is a vertisol. And because of the highly expansive clays, there's a lot of shrink and swell. So those large cracks that develop when it dries can accommodate a lot of moisture initially, but then they begin to swell. And because of that, much of the minerals and nutrients are still within the soil profile, within the rooting zone, so they tend to be very fertile soils. And soil horizons. Together, the soil horizons at a particular location make up a soil profile. Sometimes there will be an O horizon or an organic, a horizon that's dominated by organic matter. Out here in the Trans-Pecos, that typically is absent. We just don't have um, enough rainfall to grow enough vegetation to accumulate an O horizon. The A horizon is the topsoil, and then below that are subsurface horizons. You may have 3 B horizons, a B1, a B2, and a B3. Um, Below that, there will be a horizon with bedrock in it and probably some large fragments, but clearly the bedrock has begun to weather. And then below that will be consolidated hard bedrock, or an R horizon. Now, in some areas, especially really humid regions, there will also be an E horizon. And that is due to eluviation of soil minerals um, like iron and aluminum from one horizon to the horizon below it, which is the zone of eluviation. So E horizons are quite distinct, not really common in semi-arid regions though. Another horizon that many of us in Texas and other semi-arid and arid regions are familiar with is a Caliche horizon or a calcic horizon. And those typically in semi-arid and arid regions develop over thousands of years because the rainfall amount is very small. When the rain hits the soil surface, it dissolves particles of calcium carbonate, and those particles move down into the soil with the rainfall, and then that moisture is re-evaporated and the calcium carbonate is left behind. And so it takes thousands, hundreds of thousands of years to accumulate thick deposits of caliche or thick calcic horizons. And oftentimes the calcic horizon will be fairly soft, but when it's very hard, like a rock, we call that a petrocalcic horizon. So caliche is an example of a zone of, or alluvial with an I horizon. So we've talked a little bit about what is in the soil and a little bit about how we describe it, but where does it come from? Well, it looks like it comes from rock, right? It's just little bitty bits of rock. And you may remember from probably elementary school discussion about erosion and weathering. Well, there are different kinds of weathering, including biological weathering, which is carried out by plant roots, soil microorganisms, and then there's chemical weathering. Typically, it's dissolution, like we see in karst landscapes, Edwards Plateau, Edwards Limestone. And then there's mechanical weathering. And a really good example of that is glaciation or glacial soils. That's just a great characteristic or example of mechanical weathering. So soil formation. Those of us who enjoy talking about soils, we know there are 5 soil forming factors, and those are climate, parent material, organisms, relief, and time. Now, climate really determines the nature of weathering, whether it's physical or chemical or biological. Typically, physical weathering is a lot more common in cold, dry climates, whereas, like you might expect, chemical weathering is more predominant in warm, moist climates. The parent material also plays a really important role, and we're going to go into that in the next couple of slides. And we've already talked about the importance of organisms. Relief, that's basically the topography. So very steep, complex landscapes, they tend to develop and form soil a little bit differently than very flat landscapes. And time. It depends on how long a particular rock fragment or rock outcrop has been exposed to weathering as to the type and depth of soil that will form there. So parent material, this is something I really get excited about. This is a picture of Cretaceous age Glen Rose limestone. This is at the Canyon Lake Gorge. In 2002, there was some pretty widespread intense flooding on the Guadalupe River, and the dam did not fail, but water went around the dam through the spillway and just created this amazing gorge, which has been a real treat to see the material that it removed, the material that it transported. It's just it's a great place to visit. So if you have an opportunity, I don't think you'll regret it. But we know that limestone typically forms fairly light colored soils with a relatively high pH because of the concentration of calcium carbonate. And I mentioned earlier that chemical weathering or dissolution is really common with limestone because it is water soluble. So we get fractures and then we get solution features like sinkholes and caves. So it is fairly easily weathered. Sandstone, on the other hand, is not. It's much more resistant to weathering. And so typically it just takes longer to develop a soil over a sandstone parent material. And this is actually Triassic sandstone. This is Santa Rosa sandstone, and this is an outcrop in the Texas Panhandle. Now, we have a lot of Santa Rosa sandstone even throughout the Trans-Pecos, but it's buried several hundred meters below. So this is kind of a treat to be able to see an outcrop. Now this is Permian Age Limestone. This is part of the Capitan Reef complex. And some of you might recognize this as being in Guadalupe National Park. And you can see that this has developed some soil here along the toe slope. This reef actually was buried very deep, and then there was a major uplift that basically thrust it about 4,000 feet above land surface. So that also was a real treat, a nice opportunity to look at this ancient reef. Okay, and here is another example of sandstone. I'm sure some of you have heard of the Edwards Trinity Aquifer. The Trinity unit is below the Edwards limestone, and Trinity is a sandstone. It's called antler sands elsewhere. But again, it is fairly resistant to weathering, so it takes a long time to form a soil from sandstone parent material. So after these particles become weathered and the parent material begins to break down, those particles are transported somewhere, most often by water and wind, but also by gravity and ice. And here are a couple of examples of some fluvial or alluvial soils. You can see this is the Canadian River floodplain up in the Panhandle. So all of this soil in here is continually eroded and deposited from upstream to downstream. This here, over in the lower right-hand corner, these are flood deposits along the Pecos River. We had a big flood in 2014, just last fall. So we have a new accumulation of all of this soil. So it just shows that, you know, sometimes landscape formation happens very, very slowly, and then sometimes we have these big events that deposit 2.5 inches of soil. Well, that's amazing. That's a major landscape change. So we have all this new deposit near Orla, Texas, on the Pecos River, but this soil came from somewhere upstream where there was a major loss of soil. Aeolian soils are those that are transported and deposited by wind, and unlike those moved by water, these can be moved in any direction, not just downstream. And they're really common in dry regions where there's not a lot of vegetation to protect the soil surface. And this is an example that probably another one some of you are quite familiar with, White Sands National Monument in New Mexico. Another type of soil transport and deposition is a colluvial soil. And these can be found along steep slopes. Typically, the fragments are very angular. You'll notice they just haven't been transported far enough that they've become smooth or rounded. They're transported by gravity, so as opposed to the aeolian by wind or fluvial by water, colluvial soils are basically something causes a chunk to break off of this rock outcrop and then it rolls downhill. And this is a good example of physical weathering as well. Those slopes that are very active that you might see, say, driving through the Rocky Mountains, they have little to no plant cover because they are so active. And then glacial drift and till. I haven't spent much time at all on glacial soils, very limited, because in the United States they're quite a ways to the north, and still we have active glaciation, especially in Alaska. And it's a great example of physical weathering. And in the Corn Belt, we're really fortunate to have these very thick deposits of glacial till. They're relatively young, so they're still quite fertile, and they're also quite level. So it has been a very rich resource for the United States for food production. And then lastly, we have residual soils, and they are much less common. Only about 5% of soils in the United States are residual soils, or those that actually formed in place. They weren't transported from somewhere else. They just developed in place from the bedrock below them. So Pete, we have our first question. And what I'd like to know is if you remember, what is the definition of eluviation? Is it A, aerating the soil, B, adding organic matter to the soil, or C, leaching of soil material from an upper horizon to a deeper horizon? Okay. So I see there's a little bit of fluctuation still, and not everybody has answered. But it looks like the overwhelming majority says that eluviation is leaching of a soil material or soil mineral from an upper horizon to a deeper horizon. And yes, the correct answer is C. Great. And Pete, do we have any questions? If not,
No, I don't see
no.
any questions been typed out yet. And again,
Okay.
we ask our attendees have any questions. Y'all feel free to type them out. We'll be glad to answer them.
Great. Thank you very much. So we've talked a little bit about what is soil and where does it come from. And now we'll go into a little more detail about some specific characteristics, those that really distinguish one soil from another and play a really important role in the productivity of a particular site. So one of the first things that people notice about soil, if they happen to notice it, is the color, especially if it's not brown. You know, if it's red or white or yellow, or maybe even green, like this green sand from the green sand beach in Hawaii, that something kind of out of the ordinary tends to catch our eye. The green here is olivine, which is a naturally occurring mineral in the volcanic flow from the island. And another thing you'll notice about this is the grains are very large. They're very visible to the naked eye, and that these are all sand particles that we can see. Another thing that's kind of distinctive sometimes is the soil structure. And these are actually lacustrine or lake bed deposits. They're very old, but they were laid down in layers, and so now we have a soil that has a very platy structure, but it's very distinct and noticeable to someone who might be interested. So soil color, I can tell you that almost all of the soils in the Trans-Pecos can be just, they're all going to be in this 10YR family. And what we use to describe soils is the Munsell color chart. Um, and basically the color consists of a hue. It's either red, yellow, green, blue, or purple. And a value, which describes its lightness. And then a chroma, which describes the saturation. And color can be an indicator of things, especially organic matter, or minerals like gypsum and iron have a really strong influence. Those are our predominant ones that we find at least in the Trans-Pecos. Particle size. Now I hear people say, including my husband, he thinks that sand is different than soil, or dirt is what he usually calls it. But sand is just a particle size, as are silt and clay. Sand particles are visible to the naked eye. Silt and clay particles are not. This shows kind of the relative magnitude of these, and clay particles are 2 microns or less. 2 microns or 0.002 millimeters is not visible to the naked eye. For a frame of reference, a human hair, kind of the average, is about 100 microns in diameter versus 2 microns for a clay particle. Silt particles are 2 microns up to 5 microns, and then sand is 5 microns up to 2 millimeters. 2 millimeters would be like double the thickness of your fingernail, for example. Anything larger than 2 millimeters, larger than a sand particle, we do not describe as soil or fine earth. Those are rock fragments. They may be pebbles or cobbles or boulders, depending on the size. So the relative amounts of sand, silt, and clay particles in a particular soil determines what the texture is. And there are a couple of different versions of the textural triangle, but this one here is the one that I use most often. And after I've conducted a laboratory analysis of a soil sample and I have computed the relative percentages of sand, silt, and clay, then I can determine the texture. And you always start with sand first. So for example, if we had a lab sample that had 15% sand and 35% clay and 50% silt, that would be a silty clay loam texture. And loamy soils typically have almost equal percentages of sand, silt, and clay. So that's why we find them kind of here in the middle. But again, we look at our sand content and then our clay, and lastly the silt to determine the texture. And of course there are non-laboratory methods to help determine what a texture is. The texture by feel method is one of those that you may have actually conducted. And sometimes those are more than adequate to answer your question. So in addition to soil texture, at the larger scale is soil structure. And it has a very strong influence on water infiltration, water storage, and root distribution. Granular structure really is kind of the desirable structure. Blocky structure tends to be adequate, but the PEDs, or the clumps of soil, typically are a little bit larger, which means our pore space is a little bit less, our space to accommodate air and water. Platy structure, it's very difficult, as you can imagine, for water to infiltrate a platy soil, especially to infiltrate very deeply, just because the pathway is very circuitous or tortuous. Prismatic soils, kind of like the one shown here, they typically absorb a lot of water very quickly, say at the beginning of a rain event, but then begin to swell and have a reduced infiltration capacity once the swelling has begun. Massive soils are typically definitely not an arable soil, definitely not a cropland soil. And those that are structureless, oftentimes from some type of salt or other mineral present in the soil, soils that have no structure are very, very difficult to work with and tend to also be low in plant productivity. So structure plays an important role in porosity, texture and structure both. And it's mainly because not only the relative amounts of sand, silt, and clay, but the shape of those particles is really important. So size and shape both are important. And it's not just how many pores there are, but also how well connected they are. So these voids, pores are where the air and water are stored in the soil for plant use. Macropores are visible. You could pick up a ped or a small clump of soil, and oftentimes you will see little holes in there. Those are macropores, and they drain very quickly. Micropores that are microscopic, you can't see them. That is where water for future plant use is stored. And so this kind of gives us, if you might imagine this letter A here would represent a sandy soil where we have a lot of large, fairly uniform particles and some large gaps, but not a lot of small gaps. Whereas B has kind of a combination of both, which for plant production would be more desirable. And C also has some fairly large spaces, and they are pretty well connected. There's some spots here where air and water can move in between these particles. D is kind of like a vesicular soil where we have the soil matrix in black, and then we have these little holes in it that are not connected to anything. So it's very difficult for water to enter these pores and exit. So not good for plant production. And here's sort of a blocky structured soil. Again, the pores are connected, so that's desirable, and these are less well connected here. Just to kind of illustrate the importance not only of how many pores there are, but the shape and the connectivity really impacts how water can move through the soil. So we'll take a break here for our second question. Aeolian soils are those that are transported by A, wind, B, rainfall, or C, streams.
As they answer that, no questions yet. Attendees, participants, if you have any questions, feel free to type them out in the chat pod.
Okay, great. Thank you, Pete. So, the majority of you answered wind, and that is correct. Aeolian soils, and sometimes Aeolian is spelled with an A at the beginning also, kind of like Aesop. So, anyway, yes, those are soils that are transported and deposited by wind. So, soil and rangeland productivity. This is a beautiful picture, isn't it? This is in Jeff Davis County, and my hometown is right at the base of this mountain here. I was raised in Fort Davis, and I was out there last week during a nature appreciation workshop and got some great photos. So. I'd like to start off with discussion of productivity with the law of minimum, or Liebig's law of minimum. And basically, the whole premise is the amount of total resources available for plant production are not as important as the most limiting or the scarcest resource. So the level of plant production on a particular landscape or in a pasture is more strongly controlled by the scarcest resource as opposed to the amount of total resources. And sometimes the limiting resource might be nitrogen or potassium, calcium, or the other macronutrients. It could be sunlight or air, but I would say on Texas rangelands, it's almost always going to be water is the limiting factor on plant production, meaning rainfall or lack thereof. So soil definitely is the key to rangeland health. It is your most precious resource. Not a registered bull herd or a new combine or new fences. Those are great, great assets to have, but none of those would matter if you didn't have a soil resource that allowed you to grow plants on your property. And soil is the key not only to rangeland health, but to plant health. It provides physical support for the plants. It provides air and water and nutrients, all of the things that we described, and those are essential for plant growth. So knowing that water is often that limiting factor on rangelands, I get really excited about studying a particular soil and its physical properties to understand how much water it can absorb, how much water it can store, and how much is available for plant use. You know, for example, sand can absorb a whole lot of water, but it doesn't store water for a long time because it has those large pores that drain quickly. Clay can store a lot of water, but not all of that is going to be available for plant uptake just because of the particle size and the tension of water and those particles. And we know that texture and structure are really important because we've talked a lot about that in the previous slides. Organic matter also is important because it helps to improve soil structure and thus water absorption and storage. Rock content is something that some of you might not think about if you don't have very rocky soils, but rocks typically do not absorb and store a lot of water, but they do occupy space in your soil profile. So soils with a high rock content typically do not have much water storage capacity. And soil depth, obviously, if you have a very deep soil profile, you have a lot of storage capacity. So this picture here was taken in Big Bend National Park, and this is the soil surface here. You could see a grass plant there, probably red grama or something like that. And then you can see the soil, and then here we've hit bedrock. This is kind of a wavy boundary, but we have, I don't know, anywhere from 4 to 6 inches of soil with a fairly high rock content. So the storage capacity here is very low, which means this site will never support mid-grasses or large shrubs or trees. It will support short grasses like red grama, fluff grass, burrow grass, perhaps some threons. And it's quite different when you look at this soil here. I actually got this photo off the internet. It's a soil profile in Minnesota, and it's very, very thick. You could see this sharpshooter here. This is an amazing accumulation of soil. What you'll also notice are these white streaks, and that's an accumulation of calcium carbonate at depth. The presence of these streaks here also gives you some idea about how deep the water typically percolates, which is quite deep. These are both sandy soils here. You can see two horizons. So we have a lot of absorption here and a lot of storage as well. Quite a soil. So just to kind of reiterate, thinking at the very small scale, when we have a soil that is saturated, all of those pore spaces are filled with this blue water here. After about 24 hours, the soil, all of those macropores or large pores will drain to what we call field capacity. And then the soil continues to dry. Plants, there's evaporative demands from temperature and wind, plant root uptake. The soil continues to dry to permanent wilting point. And this varies depending on the texture, but it's what we term minus 15 bars, and then which is a negative pressure. So the basically the suction of water from the soil. So down here in this blue box, just to give you a perspective, a typical sandy soil has about 40% pore space. When it drains to field capacity, it has about 12% water content, and then only about 9% remains in the micropores, or that's available for plant uptake. Whereas a silt loam, I mentioned that a loamy soil is basically equal components of sand, silt, and clay. It's kind of the most desirable, primarily because of its porosity and water holding characteristics. But a silt loam has about 45% pore space, 30% water at field capacity, but 20% moisture available for plant uptake. In clay soils, we know that they can absorb a lot of water. They do have a high porosity. They maintain and they have a lot of micropores as well, 35% water at field capacity, but only 17% available for plant uptake. And that is because the water is held very tightly to those particles. And plants often cannot extract as much water from a clayey soil. And the permanent wilting point varies by soil and also for different plants. Some plants are able to extract water from the soil at very high suction or very high matrix potential. Okay, so our last question before we kind of move away from the science of soil. What is the name of the Texas state soil? And it looks like the votes are coming in. Is it a Reagan silt loam, an Altuda loamy clay, or the Houston black? Okay. A C is the correct answer. Houston black is our Texas state soil, found on the Blackland Prairie. It's a nice thick vertisol. Okay, so just to kind of summarize this front portion of our discussion, soil is comprised of both mineral and organic matter, and the soil pores are occupied by varying amounts of air and water, depending on when the last rainfall event was. So it's about 50% mineral organic, 50% pore space in general. Soils develop from a variety of parent materials, and that parent material has a very strong control on texture, structure, depth, and color. Most soils, especially in the United States, are transported by wind and water. Texture, structure, and depth also determine plant productivity. Loamy soils are optimal for plant growth, and as an example, an inch of rainfall on a loamy soil will supply plant growth for about a week during peak water demand. Okay, so now we're going to move on to just a couple of techie tools that you can use to learn more about your soil on your property. And I'm going to start off with an iPhone app called Soil Web. And it actually was developed by the California Soil Resource Lab at UC Davis. It is a free app. I am not aware that they have an Android version. I downloaded this app some time ago, but when I was searching for the URL, I did not notice that they have an Android version. But if you want to find it, you just go to the iTunes store, click on the App Store, and type in Soil Web, kind of all one word like this, and download it. So I have it on my phone, and these 1, 2, 3 here are screenshots from my phone. So when I click on the app on my phone and open it up, this is the default screen that everyone will get. And when you're outside, kind of in the open where you can get a good signal, just click on Get My Location. And once it has about 100-meter accuracy, it will pull up the soil that you are standing on. And in my case, it's the Reeker. And yes, that sounds familiar. I could agree with that. And it will pull up what a typical ped-on looks like. So we see that it has an A1 horizon, an A2, BKW1, BKW2, and a BK1 and BK2. We can also get information by each of those horizons, such as organic matter content, sand, silt, and clay content. We can get some ecological information like a plant list that occurs here. Also the soil taxonomy for this particular soil. So there is a wealth of information that's available there. It loads very quickly. As long as you have a cell signal, you can use this out in the field. Now, Web Soil Survey is quite different. It is a massive database. It has national soil survey data in it and state soil survey data within it for the whole country and territories. And it is a very powerful tool. There are many features of it that I have not used, and this is the URL for it. So if you were to pull up the Web Soil Survey and click on that in Google, for example, this is the screen that you would see first. And you would just click on this green button to launch it. Now, I will tell you that there is an app, I believe, for this now, but this is somewhat unstable. So if you use it, just be patient. Let everything load completely. You may occasionally have to refresh. But as you narrow down your geographic area, it becomes a little more stable. I guess, I don't know this, but perhaps it kind of weeds out all that extraneous data that makes it so unstable. But the first thing that you're going to want to do is locate your area of interest. And you can do this a lot of different ways. I typically go to the state and county where I can drop down a list and select Texas and then select their respective county that I'm looking for. There are other ways. You could put in some geographic coordinates. You can import an area of interest as a shapefile, for example, if you've created a shapefile in ArcGIS. So there are different ways that you can locate your area of interest.
The question came in from Norman. Says, what does slope mean on the WSS, which would be the Web Soil Survey?
I don't know if it's something that you've seen here on this page, on this particular slide that we're looking at, or if you've seen that within the platform and without some more information, I don't know
Melissa
exactly what you're referring
to.
to.
There is an app for the Android phones for the Soil Web. It's on Google Play.
Great. Thank you, Melissa. That's great to know. So back to our AOI, or area of interest. Now you can delineate an AOI up to 100,000 acres, which is huge. And you do that either by selecting this rectangular AOI button right here, or a polygon. If you want just a rectangular shape like I have here, you just click on the map and drag a rectangle over your area, and then it creates this hatched looking rectangle, which is now your AOI, or area of interest. You can also name your area of interest. You can export it as a shapefile. You can also save it as a bookmark in your browser, and I've had varying degrees of luck with that. Sometimes it saves it and I can go back to it, sometimes it doesn't. And there is a tutorial, of course, with Web Soil Survey, and as I mentioned, it has many capabilities that I have not used yet. And Norman, I see your comment again that it's within the platform regarding types of soils. So if you happen to see that as we click through here, then we can maybe take can't take a look because we're not live with the web soil survey, but I may be able to answer your question. Some other handy tools that I will mention right now on this AOI page is the ruler right here, similar to Google Earth. So if you know that you want to add a fence line somewhere, you can measure that out and get some idea about the distance. There's also an identify feature, this little blue circle with an eye. So if you click on that and then click within your area of interest, it will pull up information about that particular latitude and longitude. So the first thing I typically like to do is view the soil map. So here's the AOI tab. We've delineated that. Now we can go onto our soil map, and it will pull up a bunch of different polygons, or these squiggly orange lines that are delineated with different numbers. And those are our map unit symbols and our map units. And you can also, I will mention, on these different screens, you can actually print, or it will take you to a printable version. Another thing that you might want to consider is making some minor adjustments to the legend. If you click here on this legend tab, it will pull up this menu, and you can right click on some of these features and change, for example, the size of the map unit symbols. I made them extra large now, so what you see at the right is the extra large version. You can also change the thickness of the lines, which would be these polygon lines. So there's a limited amount of changes that you can make to your display options.
I think Norman saw the percent slopes on the previous slide.
I see the comment, and I'm sorry, but I still, without having a discussion, I'm not really sure what the question is. Slope is the percent slope or degree or the steepness of the land surface. That probably doesn't answer your question, but just in case, that's the best answer I can give without knowing the specific question. So another thing, for example, if you want to know what the texture of a particular soil is, you can go to soil reports. Now this will be in Soil Data Explorer and then in soil reports. And over to the left there will be a menu. If you select the physical properties, you can also get a soil report on particle size and coarse fragments, and it will look like this. So for each horizon of that particular soil, we will get the thickness 0 to 8 inches, 8 to 24 inches, which would be a 2-inch thick horizon, sand, silt, and clay, and the amount of rock fragments and the size of rock fragments. To learn more about a particular map unit, you would go back to your soil map and scroll down to the particular map unit that you are interested in. Okay, you may be interested in drilling a well, or setting a new tank, or installing a pipeline. Various improvements would require you to have a little bit of information about the soils, and many other engineering questions as well. But let's see. So for example, I have selected this map unit number 45, which is a true fine sandy loam on 1 to 5% slopes. And it is an eroded soil, it says. So if I click on that, this is what comes up. A very long description. You're only seeing a small portion of the screenshot. Again, I hesitated to go live there during this presentation because that platform is very unstable. Among the things that you will find in the map unit description are the ecological site. And this is really handy for many of you who are especially interested in the kinds of plants that are growing on your site or that historically grew on your piece of property. And this says the ecological site for the Truce Fine Sandy Loam is a tight sandy loam ecological site. So I can dig a little bit further and find out more about this ecological site in Soil Data Explorer, Ecological Site Assessment. And basically what I would do is scroll down to that truce or the tight sandy loam, and I've actually selected the post oak savanna midgrass community. So I get a whole list of midgrasses, short grasses, and also productivity. So it looks like annual production on this site would be about 2,000 pounds per acre, but as much as 4,000 pounds per acre. I would expect to see side oats grama, cane bluestem, little bluestem, perhaps some buffalo grass, curly mesquite. So it tells you a lot about the plant community, and many times as far as rangeland productivity, that's really what we're interested in. Some other things like for engineering or construction, you can find that kind of information just like in the old printed soil survey. That also is here in Soil Data Explorer under Suitabilities and Limitations. For example, if we want to know, we're looking at part of the ranch to put up a hunting cabin and we know it's going to need a septic tank. Well, the septic tank needs to be close to the building, but what's the suitability for the leach field? So we can look under that suitabilities and limitations and go down to sanitary facilities and septic tank absorption field. And it will pull up this information. And the rating is what we're interested in. See, here is where you would click View Rating. Then it generates a table. So it says on this clay loam, we're not limited. On this fine sandy loam that apparently has is a very shallow soil, we have limited rating for, or a very limited rating for an absorption field. Not limited here on this May very fine sandy loam. So it gives you some information for practical engineering applications as well. Now I don't know if any of you noticed, but on the AOI, the area of interest that I had delineated to use for this example, kind of in the northeast corner, there's a lot of cleared land. It looks like just some improved pasture, dry land. So let's say we want to know about vegetative productivity, yield of non-irrigated crops. This also is in the same suitabilities and limitations use tab, but you can see it's below sanitary facilities in this drop-down menu. So I clicked on that and then just went down to yield of non-irrigated crops because I know that whatever I'm going to grow is going to be dry land. And it turns out that improved Bermuda grass was an option, which is kind of what I was interested in. I know they raise a lot of coastal hay over there, and it happens to be that's one of our choices here. So this tells you for that whole area of interest and for every map unit a rating in animal unit months. So we could kind of know what type of grazing we can expect in an average year from a soil for non-irrigated improved Bermuda grass. So we have, for example, some that's fairly low productivity. This Shavash Stony Loam Fine Sand is only 3.5 animal unit months rating versus one that's this frequently flooded soil. Santo and Bunyan is up to 7 animal unit months. The bosky clay loam, probably a very productive deep soil, occasionally flooded, has a much higher rating. And it also will generate a map in addition to that table So not surprisingly, what we're looking at are mostly the red and the green is where the highest animal unit month ratings are. And that also happens to be where most of that improved pasture exists. So I'm going to end with this slide, which has a URL for the iPhone app. But again, it's much easier just to search in the iTunes App Store for Soil Web. And this is the web address for Web Soil Survey. But I would also like to add, I thought of it this morning after the slides were already loaded. If the printed soil surveys and Web Soil Survey both are designed to be used at a fairly broad scale. Now, those surveys were generated based on sample points. They cannot sample every part of a county. So if you have questions that are very specific to your property, they may require a sample from your property to get you the best answer. And your county extension agent can help you with soil sampling and preparation and shipping it to the Texas A&M University Soil, Water, and Forage Testing Lab. And all of their forms are online, and the TAMU Soil, Water, and Forage Testing Lab web address is soiltesting.tamu.edu. And with the sample form that they have on their website, you can describe what kind of information you're needing, what analyses you would like, and what you intend to do with the property, or what is your soil application. And I see that it looks like maybe I answered Norman's question. Probably not. You're welcome to call me, Norman, and I will see if I can really answer your question about slopes. My office number is 432-336-8585. And I see Howard says something about the iPhone app. Now, Howard, if you're sitting inside, your iPhone Soil Web app may just be grinding and grinding trying to get your location. If you walk outside, though, in an area that's clear overhead, and wait a few minutes, you probably can make it work. Now, I haven't used it today. You may be right. It could be down today. But anyway, good luck, Howard.
Okay,
So, Pete, I'm
thank
going to
you
turn it back
much.
over to you.
You should have you also have a satisfactory survey pop up. Please answer the survey for us, and your responses are anonymous, and it will lead to good information for us. And again, the Texas Range webinar, upcoming webinar, our next webinar is going to be on December the 3rd, 2015. And Dr. Baron Rector is going to be our speaker. There's going to be one CEU IPM attached with it. And the topic is going to be do-it-yourself brush control equipment. So I'm looking forward to Dr. Baron Rector in December. And again, we have one CEU attached to it. Again, Dr. McDonald, thank you. Very good. I learned a lot. And I guess what I'll do right now is I'll kind of sit back and see any, and for our audience that attended today, thank you all for attending. Like I say, if you have any questions, feel free to contact us. If you can't contact us, contact your county agent. He or she will be able to locate us. With that, Dr. McDonald, thank you. Enjoyed it. And see if we have any questions.
You bet. Thank you, Pete. So I'll hang on for just a minute. I don't anticipate any more, but yeah, thank y'all for joining me. It was fun.